Welcome to this session once again. So, we have already I quantified the we are writing the modeling equations for the reverse osmosis systems and the dense membranes, where the osmotic pressure plays very important role. In the last class, we have seen what is the flow transport model for quantifying the permeate flux through the membrane. Now, of the permeate transport flux of the solvent, which is basically the volumetric permeate flux through the membrane. Now, in this class we will derive what is the solute flux through the membrane. So, again we will be doing the solute flux through the membrane, starting from basic equations of irreversible thermodynamics. Okay. And the assumptions remain the same. It is a steady state system, one dimensional and no coupling. No coupling. If we now really do that, then the previous equation for the solute flux, what we will be doing, we can integrate it out. We have already done earlier that N1 dx is minus L11 C1m prime to C1m double prime del mu 1 del C1m at constant pressure and temperature d C1m plus del mu 1 del p constant temperature n times dp. So, we have already derived the expression for the governing equation of the solute and the governing equation of the solvent. So, I have omitted a step. So, we have the gradient of C1m dCm1m dx and dp dx, that we have multiplied both sides by dx, and now we are integrating it out. So, if we really do that, if we just integrate it out from 0 to L, and assuming the steady state, it will be N1 times L. Okay. Before doing that, we will be doing some simplification. For dilute solution, we can write that activity in the membrane of the solute in the membrane phase will be equivalent to concentration of solute in the membrane phase, and chemical potential can be written as mu is equal to mu naught plus R T ln A 1 m, which will be nothing but mu naught plus R T ln C 1 m. Now, let us look into the derivative of chemical potential with respect to C 1 m. So, what it gives is that this gives R T del ln C 1 m divided by del C 1 m. After that, what we are going to do? So, we will be replacing this by the definition of the molar volume of the solute, and if you really do that, so we will be replacing is by definition of solute molar volume, and after substituting this definition of solute molar volume here and del mu del Cm del mu 1 del Cm C1m in this expression, then we can get the final expression of the solute flux as N1L is equal to L11 RT ln C1m prime divided by C1m double prime plus V1 bar L11 delta P, where delta P is the P2 minus P1, that is the pressure gradient. So, N1 will be nothing but L11 RT over L ln C1m prime divided by C1m double prime plus V1 bar L11 divided by L delta P. In most of the cases, the second term will be negligibly 0, and you will be getting the expression of solute flux as L11 RT over L ln C1 m prime divided by C1 m double prime. Okay. So, this is the expression of solute flux, and again this will be having a unit moles per meter square per unit time. Now, this can be further simplified for a dilute case, for a dilute permeation stream. Why it will be a dilute permeate stream? Because that is very important in case of reverse osmosis, because in case of reverse osmosis we are talking of separation of salts to a tune of 95 to 98%. So, the permeate that is coming out of the reverse osmosis system will be very dilute, its salt concentration will be very less, it will be close to the water solution. So, we can always take an assumption of very dilute permeate stream. Under this condition, L11 can be replaced as D1m multiplied by C1m average. So, what is D1m? D1m is nothing but the solute diffusivity in the membrane phase or the solid phase. And what is C1m average? It is the average concentration of solute in membrane phase. So, once we have this assumption of dilute permeate stream, then let us look how our solute flux looks like. So, N1 can be minus L11 del mu 1 del C1 m gradient of C1 m. We neglect the second term on depending on the pressure. So, minus L11 I can write D1 m C1 m del mu 1 del C1 m gradient of C1 m, and this can be written as minus D1 m R T d ln C1 m d C1 m C1 m d C1 m dx, and this can be replaced as written as minus D1 m R T C1 m d ln C1 m divided by dx, and final expression after integration will be nothing but N1 L is equal to minus D1 m R T d C1 m integration from C1 m prime to C1 m double prime, and these will be nothing but D1 m R T C1 m prime minus C1 m double prime. The minus sign will be included in the parenthesis. So, N1 turns out to be D1 m R T over L C1 m prime minus C1 m double prime. So, these will be constant, R is universal gas constant and T is the temperature, L is the thickness. So, N1 can be K times S C1 m minus C1 m double prime. So, therefore, the solute flux will be proportional to the concentration difference. Now, if you look into the solvent flux through the membrane, is basically the membrane permeability multiplied by the effective pressure difference. So, delta P minus delta pi. On the other hand, in case of the solute flux is proportional to the difference in concentration across the membrane. Solute concentration in the upstream minus solute concentration in the downstream multiplied by a proportionality constant Ks. So, this quantifies the concentration, the transport laws of solute and solvent through the porous membrane. Now, let us quantify the permeate flux volume in the term of volumetric permeate flux. So, volumetric solvent flux will be nothing but L P times delta P minus delta pi, that we have already talked about earlier, and the solute flux N1 is K S multiplied by C 1 prime minus C 1 m double prime, and what is N 1? It is the solute flux. Now, we express the solute flux in terms of solvent flux. So, in terms of solvent flux is basically the amount of solute that will be carried, that will be entrained, that will be carried away with the solvent flow. So, what is that? This will be nothing but V w times C 1 m double prime. So, that will be the amount of solute, or that will be carried out with the solvent. So, it is basically the solute flux. This will be equal to N 1. So, you can write V w C 1 m double prime is equal to K S C 1 m prime minus C 1 m double prime, and we can now invoke the definition of retention. So, it will be, in this case it will be real retention, and the real retention is basically 1 minus C p. C p is the solute concentration in the filtrate side. So, C 1 m prime divided by C 1 m prime double prime divided by prime. So, if you really do that and express the permeate flux in terms of this, you will be getting V w is equal to B 1 minus R naught minus 1. So, it will be B R naught divided by 1 minus R naught. So, B is again some kind of constant what will be obtained from here. Okay. So, these are, and also you know the what is the solvent flux, it will be obtained from this equation. So, therefore, you can write V w is equal to L p del p minus del pi. Now, we can equate these two equation and can obtain the expression of real, in fact, this will be not the observed retention, this will be the real retention, and the expression of real retention can be obtained by this. So, what is the, by combining these two, omitting a step in between, the final expression of retention will be L p del p minus del pi is equal to, after simplification we will be getting this expression del p minus del pi plus B. Okay. This shows that at very high values of, for high values of delta p, okay, where the delta pi will be negligible. Okay. So, this term will be dominant and B will be less dominant, and R r will be approaching to 1. So, therefore, if you plot R r versus delta p, these will be approaching to 1. So, this will be approaching to 1. So, delta p, or you can plot permeate flux, because permeate flux is also proportional to delta p. So, this shows that as the driving force increases, as delta p increases, more solvent will be permeating through it, and but the solute concentration will be remaining same. Therefore, it will be diluted, and it keeps on diluted, and at a very high pressure it will be, the retention will be tending to 1. Okay. So, that gives the physical significance of retention as a function of pressure, and once that is done, the next there will be some the transport of the solute flux through the membrane is that V w C p C m C p is equal to K solvent C m minus C p. So, now we just remove the primes etcetera. C m double prime is permeate concentration, C m is the solute concentration, C p is the permeate concentration. This equation is also known as the solution diffusion model. So, we have quantified the solvent flux through the membrane, porous media, it is the Darcy's law. That is V w is equal to L p del p minus del pi. We have quantified the solute flux through the membrane, reverse osmosis membrane. It is the solution diffusion model. given as VWCP is equal to Ks Cm minus Cp. So, these two are the transport law of solute, of solvent and solute through porous membrane. Okay. Now, next what we are going to see is that next we will be talking about the fouling of the membrane. These are the transport laws through the porous membrane, but that is not the only story, as we have already discussed earlier that there will be the flow is really occurring in a channel. In the module there is a flow channel, and at the top surface and the bottom surface the membranes are placed. That means, in the flow channel on the two boundaries the membranes are placed, and what we have quantified the transport laws of the solute and solvent through the membrane, through the porous membrane, those are situated at the boundaries or walls of the flow channel. Next, but that is not the only story. If you remember, in a previous class we have already discussed about this, that in a flow channel over the flow is taking place over the membrane, and there will be existing a concentration gradient starting from bulk concentration up to membrane surface concentration, forming a mass transfer boundary layer. So, in short we write MTBL to denote the mass transfer boundary layer. So, therefore, until now whatever we have done, we have formulated the transport laws between across the membrane from Cm and Cp in the permeate side, but we have not considered this film of mass transfer boundary layer in consideration to formulate our transport laws of the solute and the solvent. In fact, there are two resistances are involved in this process. One is the membrane. There are two media involved in the process. One is the membrane surface, one is the mass transfer boundary layer. These two are placed one after another in series, and these two will be considered. So, the polarization of the solute over the mass transfer boundary layer ranging from concentration C naught in the feed and the Cm in the on the membrane surface is known as concentration polarization. In an actual membrane separation system, this concentration polarization should be considered, and it will be function of feed concentration, transmembrane pressure drop, and cross flow velocity, because feed is flowing like this. This is known as the cross flow velocity. So, it is known as the U naught. What is cross flow velocity? The flow will be basically occurring through a rectangular channel in a spiral wound module or through a tube in a tubular module. Okay. Now, membrane is placed in case of rectangular channel on the top surface as well as on the bottom surface, and here in the tube along the surface of the tube. Now, we are pumping the fluid or the feed in the membrane channel like this, and the filtrate or the permeate comes out this from the wall, and the retentate goes from the outside the module. Now, outside the module. So, there will be a formation of mass transfer boundary layer over the membrane surface. These are mass transfer boundary layer over the membrane surface, and the concentration profile will be from C naught to Cm. From C naught to Cm, the exploded version of this has been shown here. Okay. So, we have to solve the governing equation in the channel outside the membrane, and then we have to hook it up with the flow through the porous medium, that is the situated on the boundary of the channel. So, then it will be giving a complete description of the modeling of the solute and the solvent through the membrane system, and ultimately we are going to get a system performance in terms of solvent flux and the solute concentration in the permeate. Anyway, now what is concentration polarization? The formation or accumulation of solutes over the membrane surface of solute over membrane surface is known as concentration polarization. Now, concentration polarization will lead to membrane fouling. As you must have understood that this mass transfer boundary layer will be basically offering a mass transfer resistance against the solvent flux. So, therefore, more be the thickness of mass transfer boundary layer, more be the resistance against the solvent flux, and it will be its value will be going down. And as temperature, as the time of filtration progresses or duration of filtration progresses, the concentration polarization layer builds up, decreasing the throughput with respect to time. So, one has to really calculate or quantify the decline in permeate flux, which will be ultimately causing the membrane fouling. So, once the membrane is fouled, its performance goes down and its life is decreased, and therefore, one has to basically quantify that whether the membrane fouling can be really controllable or it will be going uncontrollable, which will be if it is too much, then the throughput of the process will be too less and the commercial viability of the process will be very low. So, in that case, so we look into the in this context to look into the problem of membrane fouling. The fouling is of two types. One is the reversible fouling, another is the irreversible fouling. So, in case of reversible fouling, whatever the layer that will be deposited over the membrane surface, that will be deposited over the membrane surface, that can be washed away by adopting a proper washing protocol. So, fouling layer deposited over the membrane surface can be removed by proper washing. Fouling on membrane surface can be removed completely by washing, thereby recovering the membrane permeability completely. On the other hand, in case of irreversible fouling, there are pores in the membrane surface, and these pores can be interconnected pore. They are not necessarily the straight cylindrical pores. There are various type of pores are available in the membrane surface, in the membrane matrix, membrane cross section, and since the concentration of solute on the membrane surface is more compared to concentration of solute in the permeate site, solutes will be traveling maybe because of the diffusion, because of the concentration gradient, and since there will be a distribution of the pore size, there will be some pores always available in the membrane surface, which will be larger compared to the size of the solute, and they will be traversing on the membrane side, blocking the membrane pores partially or completely, or they may be adsorbed on the pore mouth and sitting on the pore mouth of the membrane surface, blocking that particular pore. So, all these phenomena will be causing to blocking of membrane pores. So, these are known as the pore blocking phenomena. These are known as the pore blocking phenomena. So, even after washing, after proper washing, some of the sites of the blocking may be opened, but not all. So, therefore, the pore blocking cannot be recovered completely. And therefore, some fraction of membrane permeability is permanently lost, and this is known as irreversible fouling. So, in case of irreversible fouling, even after proper washing, some fraction of permeability is permanently lost. So, it leads to permanent loss of membrane permeability. Now, we will look into the various manifestations of concentration polarization. So, if we look into the various manifestation of concentration polarization and what it really do, let us look into this concentration polarization. So, basically the effect of concentration polarization is accumulation of the solute particles over the membrane surface, thereby increasing its surface concentration. Now, let us see what this surface concentration, increase in surface concentration will do. So, Cm, membrane solute concentration on the membrane surface increases, this increases the osmotic pressure of the solution. If the osmotic pressure of the solution increases, then the effective driving force will decrease. Okay. If effective driving force will decrease, the permeate flux will decrease, the throughput of the process will decrease. Now, with increase in membrane surface concentration, in case of some solutes, the solute will surface concentration will keep on increasing, and after a particular point the solubility limit may be reached, or the solutes can be deposited over the membrane surface forming a gel. Now, gel formation can be done, gel formation can occur by two ways. One, for some solutes the solubility limit will be approached. So, this can be attained by approaching solubility limit. And secondly, for some solutes which are naturally gel forming material, they form gel from the very beginning, form gel from very beginning. For example, pectin. Pectin is an example. So, pectin is a well known gel forming agent, and this particular solute forms a gel from the very beginning of the operation. So, therefore, it forms a very viscous layer over the membrane surface, therefore, the permeate flux, so resistance increases, so permeate flux goes down. Third phenomena is increase in viscosity. So, when the concentration polarization increases, the solute concentration on the membrane surface increases tremendously, and therefore, the thermophysical properties of the solute in the system may be affected by the increase in solute concentration. What are the typical transport coefficients that appear? There are three transport coefficients appear. One is density, another is diffusivity, another is the viscosity. Now, density is the weakest function of concentration, diffusivity is a moderate function of concentration in some solutes, and it is a weak function of concentration in most of the solutes, and among this viscosity is the strongest function of concentration. In fact, viscosity is an ever increasing, is an exponential function of concentration, and typically when the Cm is in case of concentration polarization, the membrane surface concentration is 3 to 4 times in case of osmotic pressure control filtration. For the gel layer filtration, this can go as high as 50 to 100 times. Even in some case of osmotic pressure control filtration, for example, using dextran, the membrane surface concentration can be as high as 25 to 30 times the feed concentration. So, in that case, the viscosity suffered a lot. In fact, viscosity increases tremendously over the mass transfer boundary layer. So, within the mass transfer boundary layer. So, increase in viscosity, what it results? It results into a very thick, highly viscous solvent near the membrane surface. It offers additional resistance. So, resistance against the solvent flux increases by increasing mass transfer resistance, and its result is decline in permeate flux. Okay. The fourth manifestation of concentration polarization is that as the concentration polarization, as we have described earlier, that across the membrane the Cm is concentration, solute concentration on the membrane surface is high, and the solute concentration in the permeate is low. So, there exists a concentration gradient across the membrane cross section, and some solutes, because of this gradient, some solutes will be transported through the membrane pores, and during its transport they can block some of the pores permanently or partially or completely. So, it will lead to pore blocking. What is the manifestation of pore blocking? Pore blocking is manifested by reduction in membrane permeability. So, permeability, membrane permeability goes down because of the pore blocking. So, therefore, what is the effect? Since the permeate flux is proportional to permeability, the permeate flux goes down. So, we can see that the manifestation of concentration polarization in all the cases will lead to a common outcome or common result, that will be the decline in permeate flux. So, we have, because of the concentration polarization, we have a decline of permeate flux, which will be basically reduction in the throughput of the process, which is absolutely undesirable. But one cannot avoid concentration polarization completely, but one can minimize it. So, there are various ways of minimization, and in order to get a complete system performance prediction, one has to take care of transport in the flow channel and then hook it up, which have been yet to be. So, transport of the flow channel means we have to solve the solute concentration in the mass transfer boundary layer, and to quantify the concentration polarization perfectly, and then we have to hook it up with the transport laws through the porous membrane that we have already derived as in the form of solute flux and the solvent flux by Darcy's law, and solute flux through solution diffusion model through the porous medium. These two laws, transport laws, have to be hooked up with the transport laws that will be occurring in the outside the membrane surface, inside the flow channel, within the mass transfer boundary layer. So, in the next class we will be looking this connection, and then we will be completing the first dimensional modeling of one dimensional modeling of the flow through the membrane channel to have a system prediction. Thank you very much.